You've seen it. Campfires, candles, the burner on your stove clicking to life. Fire is hot, fire is bright, fire burns things. That's enough, right? You don't need to know more than that to use it. But here's what should bother you. Fire doesn't behave like anything else you interact with. Pick up a rock. It stays a rock. Pour water into a glass. It sits there, being water. But fire? Fire doesn't sit. Fire doesn't stay. Fire flows. It flickers, it dances, it spreads, it climbs walls and jumps gaps, it consumes and grows, and then eventually it dies. What is that? What kind of thing behaves like that? The answer is going to break something in your head. Fire is not a thing at all. It's not an object, it's not a substance. You cannot hold fire. You cannot weigh fire. You cannot put fire in a box the way you put water in a box. Fire is something else entirely. Fire is a process, a cascade, a catastrophe unfolding at the atomic level, perpetuating itself, feeding on itself, spreading itself. When you watch flames dance, you're watching atoms rearranging themselves in a runaway chain reaction. And the light you see, the heat you feel, that's energy being released as those atoms snap into new configurations. But let's slow down. Let's actually understand what's happening. Start with a piece of wood. Dead tree sitting on your fireplace. It's been sitting there for weeks, maybe months. The air is all around it. Oxygen molecules floating past, bumping into it constantly. Millions of collisions every second. The wood and the oxygen are right there touching each other and nothing happens. Why? This is the question most people never think to ask. The wood has carbon in it. The oxygen in the air would very much like to be attached to that carbon. Carbon and oxygen, they want to be together. Being together is the stable state, the low energy configuration. When carbon and oxygen combine, they form carbon dioxide, and that process releases energy. A lot of energy. That's where the heat comes from. So if they want to be together so badly, why don't they just combine? Why does the wood sit there for years, decades, centuries even, in the presence of oxygen, and nothing happens? Because of a barrier. Think of it like a ball on a hill. The ball is sitting in a small depression at the top of the hill. There's a deep valley below. The ball would love to roll down into that valley. That's the low energy state. But to get there, it first has to climb out of the little depression it's sitting in. It has to get over a small bump before it can fall into the deep hole. If the ball isn't moving fast enough, it can't get over that bump. It just rocks back and forth in its little depression, never escaping. It could sit there forever. That's what's happening with the wood and the oxygen. The carbon atoms and oxygen molecules are bouncing off each other constantly, millions of times per second, but at room temperature they're not moving fast enough to get over the barrier. They collide, they bounce apart, nothing happens. The ball rocks back and forth but never escapes its depression. This can go on for centuries. A piece of wood can exist in the presence of oxygen for 1,000 years and never react. The atoms are trying, they're colliding constantly. But they don't have enough energy to get over that initial hump. Now, what happens when you light a match? You're adding energy. You're making atoms move faster. You're giving them the kick they need to get over that barrier. When you heat up a small spot on the wood, you make the atoms in that region jiggle more violently. Some of them now have enough energy to climb over the bump. They get close enough to the oxygen, and they snap together. And here's where it gets interesting. When carbon and oxygen snap together, they release energy. That's the whole point. That's where the heat comes from. But that energy doesn't disappear. It doesn't vanish into nothing. It goes into the surrounding atoms. It makes them jiggle faster. It heats them up. And now those heated atoms have enough energy to react. They snap together with oxygen, releasing more energy, heating more atoms, which react and release more energy, which heats more atoms. You see what's happening? It's exponential. 1 reaction triggers 2, 2 trigger 4, 4 trigger 8. The number of reacting atoms doubles and doubles and doubles. Within a fraction of a second, you have billions of atoms all snapping together simultaneously. That's fire. That catastrophe, that runaway chain reaction. Atoms snapping together, releasing energy, making other atoms snap together, releasing more energy, on and on. Once it gets started, it feeds itself. The heat from the reactions provides the energy needed to make more reactions happen. It's self-sustaining. This is why fire flows. This is why it spreads. The reaction in one spot heats the adjacent region, which starts reacting, which heats the next region, which starts reacting. The cascade propagates outward like a wave. The fire doesn't stay in one place because the energy it releases makes it impossible to stay in one place. It has to spread. It has to flow. That's the nature of the process. And the only way to stop it is to break the loop. Cool it down below the threshold. Remove the fuel. Remove the oxygen. Cut off one leg of the triangle and the whole cascade collapses. The atoms stop reacting because they don't have enough energy anymore to get over that barrier. The fire dies. But we're not done. Not even close. Let's ask a deeper question. Where did this energy come from in the first place? When the fire burns, it releases heat and light. But that energy had to come from somewhere. Energy doesn't appear from nothing. So where was it stored? How did it get into the wood? Think about where wood comes from. It comes from a tree. And what is a tree made of? Carbon. Lots and lots of carbon, arranged into complex molecules. Cellulose, lignin, the structural materials of plants. Now, where did the tree get that carbon? Most people think it came from the ground. You plant a seed in soil, water it, and a tree grows. Obviously, the tree came from the soil, right? Wrong. Take a pot of soil, weigh it carefully, plant a seed, water it for years. Let the tree grow big and heavy. Now dig up the tree and weigh the soil again. The soil weighs almost the same as it did before, maybe a tiny bit less from some minerals that got absorbed. But the tree weighs hundreds of pounds more than it did as a seed. Where did all that mass come from? Not from the soil. The soil didn't lose hundreds of pounds. The tree came from the air. Carbon dioxide, CO2, it's in the air all around us, about 400 parts per million. Not much, but it's there, and trees pull it in through their leaves. They take that carbon dioxide and they do something remarkable. They rip it apart, they separate the carbon from the oxygen, they keep the carbon to build their structure, and they release the oxygen back into the atmosphere. That's photosynthesis. That's what plants do. They're taking carbon out of the air and turning it into solid material. The bulk of a tree, the wood, the branches, the trunk, that's carbon from the atmosphere, combined with water from the rain. Almost nothing came from the soil. But wait, I just told you that carbon and oxygen want to be together. They snap together and release energy. So how does the tree rip them apart? That should require energy. You can't separate things that want to be together without putting energy in. The sun is doing the work. Sunlight hits the leaves, and that energy gets used to drive the separation. The tree is using solar energy to pull carbon away from oxygen and build itself out of that carbon. It's pumping energy into the system. It's creating order out of disorder. It's pushing the ball back up the hill, and that energy gets stored. When the carbon is separated from oxygen and locked into the wood's molecular structure, energy is stored in that configuration. The carbon is sitting at the top of the hill, held there by the structure of the molecules. It wants to fall back down. It wants to recombine with oxygen. But it's stuck, waiting for a trigger. Now you cut down the tree. You let the wood dry. You stack it in your fireplace. And when you light it, you provide that trigger. You give the atoms enough energy to get over the barrier. And then everything the tree spent years building collapses in minutes. The carbon snaps back together with oxygen. The stored energy releases all at once. The light and heat from your fire? That's the sun. That's sunlight that fell on leaves 5 years ago, 10 years ago, 50 years ago. It got stored as chemical potential energy, locked into molecular bonds, waiting. And now it's coming back out. Fire is stored sunlight escaping. When you watch a log burn, you're watching the sun shine again. The photons coming off that flame are, in a very real sense, recycled photons from the sun. The energy is the same. It went in as sunlight, got stored as structure, and comes back out as firelight. This is why fire seems almost alive. It consumes, it grows, it spreads, it breeds, it needs fuel and oxygen just like you do. And that's not a coincidence, because at the fundamental level, fire and life are the same process. Think about what you do when you breathe. You inhale oxygen. You eat food, which contains carbon-based molecules. Inside your cells, that carbon gets combined with oxygen. Carbon dioxide gets released, energy gets extracted. That's the exact same reaction as fire. Carbon plus oxygen makes carbon dioxide and releases energy. The chemistry is identical, the only difference is speed and control. Fire does it all at once, a violent cascade. Billions of reactions happening simultaneously in a runaway chain. Your body does it slowly, carefully, one molecule at a time, capturing the energy in useful forms like ATP. But it's the same process, the same atoms rearranging, the same energy being released. You are a slow fire, a controlled burn. Your metabolism is combustion, just regulated by enzymes and cellular machinery so it doesn't run away. If your cells lost that control, if the reaction started happening all at once instead of being carefully metered out, you would literally burst into flames. The energy release would be too fast to dissipate. This is what connects everything. The sun drives photosynthesis. Photosynthesis stores energy in carbon-based molecules. Those molecules feed plants, which feed animals, which feed you. And then, through respiration, you slowly burn those molecules back into carbon dioxide, extracting the energy to power your life. Fire is the fast version of what your body does slowly. Both are oxidation. Both are carbon recombining with oxygen. Both release the energy that the sun put in. Now let's talk about why fire looks the way it does. The flickering, the colors, the dancing light. Where does that come from? When atoms snap together, they don't just release heat. They also release light. Here's how. When the reaction happens, energy gets dumped into the products. The newly formed carbon dioxide molecules are vibrating violently. The atoms are moving fast. That's what heat is, remember, atomic motion. But some of that energy also goes into the electrons around the atoms. The electrons get excited. They jump up to higher energy levels. But electrons don't like being in high energy states. They want to fall back down. And when they do, they emit photons, light. Different atoms emit different colors. Sodium atoms give off yellow light. That's why flames often have that characteristic yellow-orange color, especially when burning organic material that contains traces of sodium. Copper gives off green. Strontium gives off red. That's how fireworks work. You add different metals to the mixture, and they burn with different colors. The blue part of a flame, that comes from a different process. That's typically from carbon radicals and other intermediate species that form during combustion. They have their own characteristic emission spectra. The dancing and flickering, that's turbulence. Hot gases rise because they're less dense than cold air. As the hot combustion products rise, cool air rushes in to replace them. This creates complex, chaotic patterns of flow. Vortices form and break apart. The flame gets pulled and pushed and twisted by the moving air. It dances because it's riding on a constantly shifting current. And the sound? The crackle and pop of a fire? That's pockets of water and sap inside the wood. When they get hot enough, they turn to steam. The pressure builds until the wood structure ruptures. Pop, crackle, little explosions of steam escaping. Everything you see and hear and feel from a fire has an explanation. Not a mysterious explanation, not a vague hand wave. A real, mechanical, atomic-level explanation. The dancing is turbulence. The colors are electron transitions. The heat is atomic motion. The crackling is steam pressure release. But here's what most people miss entirely. The oxygen you're using to burn that wood, where did it come from? From trees, from plants, from photosynthesis. The early Earth had almost no free oxygen. The atmosphere was carbon dioxide, nitrogen, water vapor. Then photosynthetic organisms evolved. They started pulling carbon dioxide apart, keeping the carbon, releasing the oxygen. For billions of years, they dumped oxygen into the atmosphere as waste. Oxygen was a byproduct, a poison, actually, to many early life forms. But eventually, organisms evolved that could use that oxygen. They could burn carbon compounds with it, extracting energy. And that oxygen is what makes fire possible. So here's the full cycle. The sun shines. Plants use that sunlight to rip apart carbon dioxide. They keep the carbon and release the oxygen. Energy gets stored in the carbon compounds. Then either a fire burns those compounds or an animal eats them and slowly burns them through respiration. Either way, the carbon recombines with oxygen. Carbon dioxide gets released back into the atmosphere. Energy comes out. And the cycle repeats. The sun drives it all. The sun is the engine. Everything else is just the sun's energy being passed around, stored, released, transformed. When you sit by a fire, you're watching the sun shine. When you breathe, you're slowly burning the sun's stored energy. When you eat, you're taking in captured sunlight. The entire biosphere is just an elaborate machine for capturing, storing, and releasing solar energy. Fire makes this visible. Fire makes it obvious. The energy flow that's usually hidden, usually slow, usually distributed across countless tiny cellular reactions becomes concentrated, intense, visible. You can see the energy escaping. You can feel it hitting your skin. You can watch the stored sunlight being released. That's why fire has fascinated humans for hundreds of thousands of years. Not just because it's useful, not just because it keeps us warm and cooks our food, but because it reveals something profound about the nature of things. Fire shows you that matter is not static, that atoms are constantly in motion, that energy flows, that the world is a dynamic system of continuous transformation. Nothing stays the same. Everything is process. Even the things that look solid and permanent are just temporarily stable arrangements, waiting for the right trigger to transform into something else. A log looks permanent. It's been sitting there for months, years maybe. It seems like a thing, a static object. But it's not. It's a metastable configuration, a ball perched at the top of a hill, held there by a small barrier. Give it the right nudge and it transforms completely. The carbon that spent years being slowly assembled by the tree suddenly rearranges itself in minutes. The stored energy releases. The solid becomes gas and light and heat. This is what the world is actually like at the atomic level, not fixed, not permanent, dynamic, constantly transforming. The apparent stability you see around you is temporary. It depends on conditions. Change the conditions and everything changes. Fire is just one example, but it's the most visible example, the most dramatic, the example that humans have stared into for millennia, watching the dance, feeling the heat, not understanding what they were seeing, but sensing somehow that it mattered. Now you know. Fire is the rapid recombination of carbon and oxygen that were separated by the sun. It's stored sunlight escaping. It's the same process as respiration, just faster and uncontrolled. It flows and spreads because it's a self-sustaining chain reaction, each burst of energy triggering the next. It dies when the fuel runs out or the oxygen runs out or the temperature drops below the threshold needed to sustain the cascade. The light is electron transitions. The heat is atomic motion. The dancing is turbulence. The crackling is steam release. Every aspect has a mechanical explanation, a physical basis, a real underlying process. And when you understand all that, when you really see what's happening, fire becomes even more remarkable. Not less, more. Because now you're not just watching flames, you're watching atoms. You're watching energy. You're watching the sun's output from years past being released all at once. You're watching the fundamental processes of the universe made visible and immediate. That's what fire is, not a mystery, not magic, not an inexplicable force. A window into how matter really behaves, how energy really flows, how the cosmos really works. All you have to do is look,